Hello, my name is Kyle Mo, and today we're going to be talking about Newton's Cradles, a device not actually created by Isaac Newton, but created by English actor Simon Preble in 1967, a full 240 years after Newton's death. If you ever researched or have dived deeper into Newton's Cradles, then you probably know that it shows things like conservation of momentum or conservation of energy. And while these are great terms to describe what is happening during these collisions, there is certainly more detail that you can go into. Now, I can certainly explain the complexities of a Newton's cradle of animations, which I certainly will still do, but for added effect, me and my friend Nirmal went to Home Depot and decided to build a 7-foot tall model of a Newton's cradle with basketballs and pieces of wood. As you've probably seen, when you release one ball from a set height and it collides with the other three balls in the middle, the other ball goes flying up to the same height. Well, why is it? Well, there are many ways to explain that, but I think the simplest is through conservation of linear momentum. Imagine the ball right before the collision, and for simplicity's sake, let's number them 1 through 5, with 1 being on the very left and 5 being on the very right. But before we can do any momentum equations, though, we should really learn why we can apply conservation of momentum at this particular point. You see, we can't just choose any point on ball number 5's trajectory. In order to use conservation of momentum, we must be able to prove that there's no net external forces acting on the ball. And while this might seem like a random jumble of words, it is better explained using free body diagrams. Let's draw two of these free body diagrams, one when the ball is right about to collide, and one when it's on its downswing. If we were to analyze the free body diagram when it's right about to collide, we can see that there's two forces acting upon it. One, which is the force of gravity, F of g, and the force of tension, which in this case is equal in the opposing direction of gravity. Here, if we were to calculate the net vertical force, we can see that the tension and the gravity cancel out, and therefore there are no net external forces on the system, and therefore we can apply conservation of momentum. Take a moment when ball number 5 is on its downswing. Here we can see that gravity is still straight down, but now the force of tension is angled. In this free body diagram, we're going to have to split one of these forces into components, and if we were to keep gravity on the y-axis, we would have to split up tension. However, it is easier to understand if we swap these two, so that tension now aligns at the y-axis. We can then split up the force of gravity into its x and y components, and then we can calculate the net vertical and horizontal forces acting on the system. If we were to calculate the net vertical force, we can see that the force of tension cancels out with the y component of gravity. If we were to calculate the net horizontal force, we can see that the x component of gravity has nothing to combat it out with, and therefore there is a net force acting on the system, and therefore we cannot apply conservation of momentum. So, now that we know when and when not we can use conservation of momentum, we should finally be able to look at the momentum equation itself, which is the product of the mass and velocity. Here we can clearly see why there can't be a net force acting on the system, as a non-zero net force means a non-zero acceleration, which makes the velocity in this equation a non-constant. If momentum is conserved, then we should be able to compare the momentum before and after the collision. And if the momentum turns out to be the same, then momentum is conserved. Here, we're going to define our system as the 5 balls. Before the collision, only one ball has a non-zero velocity, which is ball number 5. Ball number 5 has a mass of m and a velocity of v, which is heading towards the left. After the collision, we can see that again only one ball has a non-zero velocity, which is ball number 1. And again, it's identical, so it has a mass of m and it has a velocity which is also heading towards the left. We can then see mathematically that momentum is conserved with mv equaling mv. What if two balls are raised though? Here we can see that the momentum right before the collision is two balls of identical mass traveling at a speed of v. So we can predict that the end result must equal 2mv. Now when we observe this happens, we see two balls coming out with a speed of v. However, why is it that two balls come out? Why can't it be that just one ball comes out with twice the speed, as mathematically that also makes sense? The answer lies within just simplifying this entire scenario with just one momentum equation. A better way to look at it is through a series of collisions. While it may look like ball 4 and 5 are connected, they are actually separated by a tiny margin. With this knowledge, I'm going to try to explain what actually happens. First, the strike is 4, which collides with 3, which then collides with 2, and so on. It is important to know that within these tiny collisions, conservation of momentum does apply. Shortly after 4 collides, though, 5 comes in and collides with 4, and the chain repeats itself. And shortly after 1 gets sent off, 2 follows, and it appears like they were sent off at the exact same time. This is why the mass gets doubled and not the velocity. Now, with all this knowledge, I encourage you to figure out what happens when 3 balls are raised. We observe that 3 balls come out, but why? Well, the same thing happens with the 2-ball collision. 5 sends out 1, 4 sends out 2, but what about ball number 3? Well, in this case, it has nothing to collide with, as 1 and 2 have already been sent out by 4 and 5. And just to bring it in, if we observe the momentum before and after, we see that 3mv is equal to 3mv, so momentum is still conserved in this situation. Anyway, there's so much more to learn about these simple devices. I encourage you, if you want to learn more, like how exactly do we know that it's the same velocity before and after, I encourage you to explore more topics, like conservation of energy, and apply it to this situation. Or, better yet, create your own Newton's Cradle and just mess around just like we did. Thanks for watching. This was created by my friend Nirmal, Karthik, and me, Kyle Mo. It would be greatly appreciated if you left a comment, you liked, you subscribed, being a newer channel, and hopefully we can keep on producing these for all of you guys.